Hello everyone, welcome to the statics course. Today we are going to learn chapter 6, which is 6.1 simple trusses. So this is the first chapter of chapter 6, truss. Truss is a very interesting structure, and there are many questions will be appeared from this chapter 6 for the midterm exam too. So I want you to keep very focusing on for this chapter. Especially the first chapter is very important because I'm going to explain some important concept to solve the truss part. So if you look at here, there is a bridge, and we can use a simple truss method to build up this bridge very easily because a truss is very solid and very simple. It has a lot of application, like not just a bridge, also roof or any structure in the space. So we can use this truss method to build structures. Today we have two learning goals. First is I want you to define a simple truss. The second is I want you to know how to determine forces in members of a simple truss. Like I said, a truss is a structure that is a shape of the triangular shape, and they are jointed together at the end of the point. So if you look at the images, they are all jointed at end point. And this one is very strong structure to hold a certain weight. So that's why we can use this truss to support the roof and the bridge when the heavy load will be applied to the bridge. Then the bridge should support the heavy load, right? So the truss is useful for building the roof and the bridges. There are two main assumptions throughout the whole this chapter 6. The first thing is all loadings are applied to at the joint. So here we have some joint here. Joint. So all the load will be applied at the joint, not the middle, okay? So all the forces will be applied at the joint. Second thing is they are connected with a pin connected. So pin connected means there will be two unknown support reactions, right? The horizontal and the vertical. So keep in mind that all the joints are connected by the smooth pin. Okay, so this is important concept. So I want you to understand this concept. There is unknown forces in truss members. The force is either it could be tensions, which is the pulling forces. So you can see that here's the end point and there are pulling forces. So this member is in tension, right? However, there is another situation. The joint are compressed. The joint is compressed by the forces. Then this member is in compression. Okay, so there are two situations. One is tension, the other one is compression. So when we calculate the main internal force in truss, then we have to make an assumption. So okay, this member may be in tension, or this member may be in compressions. We can set up the assumption, but the assumption is it's not that critical in this part, because when we do the inspections by the manual calculation, then we will figure out whether this member is actually in tension or compressions. Okay. By the way, this is a little tip, guys. when we design the member truss, if this is in compression, then this member should be designed must be thicker, right? Because the thicker one hold the weight more appropriately than the thinner one, right? So defining compression or tension is very important when we design truss. This is a simple truss. Why this is a simple truss? Because we can expand by adding two members here and here. So we can have another triangular. We have a original triangular here. We have another one, and we can add two members here and two members here. So we can expand easily. So that's why we call this is a simple truss. Here, this is an example of a simple truss. Now, we are going to apply equilibrium equation to solve the unknown forces. Here we have a simple truss. Point A is pin connected and the point C is pin connected, but here we have a support reaction that is a rocker. This is a rocker. So we already know that there are one unknown support reactions, right? How about the pin connected? We know that there are two support reactions, right? Okay. How about B? B is just the pin connected. Remember, this entire truss is in equilibrium. That means this entire simple truss is stable. Then every single joint are stable. They are in equilibrium. So we can apply this two-dimensional equilibrium equation, sigma fx equals 0, sigma fy equals 0. We can apply this rule at any joint here because they have to satisfy this rule because this entire truss is in equilibrium. Like I said, when we set up the assumptions, direction is not important. We can figure out later what is the right direction based on our assumption, based on our inspection, okay? The second thing is you have to make an assumption whether this member is in tension or compression. It's really up to you, okay? But you will figure out the right the force members after you calculate. So again, this is a simple truss. The method of joint. Today we are going to run the method of joint to calculate the internal force in truss. We will learn another method which is method of sections. Probably we will learn this concept next week or this Thursday. But let's look at the method of joint. So we are looking at the joint. Okay. Again, this entire truss is unstable. The joint B should be in equilibrium. We know that there are one known, this is not unknown, this is known external forces. There are 500 Newton pulling toward the right-hand directions. And we don't know the two forces, which is the internal force in the two-member joint. Here you can see that there are these members and these members. We don't know whether this one is in compression or tension. So let's make an assumption here. So in the textbook, they assume that the force member BA is in tensions. So that's why the 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 force is pulling from the joint B. From the joint B, it's a pulling force. Pulling, okay? And we can see that there are push force toward the B. So push toward the B means these members are in compressions. That's why it push toward the B, okay? So again, let me explain one more time. If there is a push force to the joint B, then that member is in compression, okay? And there is a pulling force, on the other hand, that is tension. Member BA is in tension, okay? So we have one known, but we have two unknowns here. One known and two unknown forces. Now we can solve the problem by applying equilibrium of equation. So let's set the orientation. Right hand direction is positive x, upper direction is positive y. We can apply these two equations. Sigma fx is equal to 0, sigma fy is equal to 0. For the x-axis component, what is the x-axis component? Here we have a positive 500 Newton and what? Right, this one. Force BC, that is toward the left-hand directions. So that's why we can set up like this, 500 Newton minus force BC times sine 45 or cosine 45 is equal to 0. Okay, so from this equation, we can find the BC, right? There is no difficulties here. For the y directions, okay, we have two unknowns are associated for the y-axis. Force BC times cosine 45, which is upward direction, so that's why it's positive, and minus force BA is equal to 0. So once we find the force BC here, force BC, we know that, then we can find force BA. Okay, so let's practice. This is the same example what we just looked at. I want you to find all the internal forces and as well as external forces. This problem is very important. I'm trying to thinking that definitely ask these questions in the midterm exam too, because this is very basic as well as this is very important. So I want you to solve these problems by yourselves. So let's try to find all the forces, internal and external forces, using the method of joint here. Okay, let me remove my keyboard. Okay. Right, let me draw the free body diagram. Is a 45 degree, that means this one is also 45 degree because this one is perpendicular. as you may know, this joint A is pin connected. So pin support has two support reactions. So let's say, okay, let's define the orientation first. Positive x, y. So AY, AX, which is unknown forces. However, joint C, this is supported by rocker. So rocker has only one support reaction. CY. Okay, so we defined all the unknown forces here. Now we're going to look at the internal forces. Let's look at the E. Okay. The joint B. We can say that. Let me redraw at joint B for your clarification. Two members are connected. But we don't know these two internal forces are in tension or compressions. So let's assume that this force is in tension and these forces are in compressions. So force, this is BA. Okay. And this is force BC. Okay. Then we can apply equilibrium equations for the member joint B. Fx should be equal to 0. Y equal to 0. For the x, we can find that 500 Newton minus FBC cosine 45 is equal to 0. For the y, force BC sine 45 minus FBA, this one is equal to 0. From the first equation, we can find that FBC is 707 Newton. Okay, and we can plug this one into here. Then we can find FBA is equal 500 Newton. Okay, but the direction, let's find a sign here. This is a positive. FBC has a positive 707 Newton and FBA has a positive. So our assumption is right. So force BC is in, we can say, compressions. We can express this way. Force BA is in tension. Now we already know that member BC is in, this member BC is in compressions. So this is 707 Newton compression. And the force BA, the member BA is in, this one is tensions, 500 Newton. This is in tension. Next question is, what is the member AC? AC is, we can try, it's a different color. C. Okay, if you look at the C, this is joint C, there is force, which is 707 Newton, force BC. There's another force, CY, and this one is force AC. By the way, what I wanted to say here is actually, you know what? We can find the CY before we start solving these problems. Why? Because this entire truss is in equilibrium. Then we can also apply another equation, that is the sigma moment at any point O should be equal to 0. Okay, in this case O is point A. So when you calculate the moment, the entire truss, the moment of this entire truss, there is a 500 Newton external forces which create a clockwise rotation at point A, and this CY create a counterclockwise rotations. So it will be cancelled out. Let's see, moment at A should be equal to 0. This 500 Newton create counterclockwise, never mind, it's clockwise rotation. So 500 Newton times 2 meter, which is a perpendicular distance from A to B, and this is a minus, and the plus CY, we also have a 2 meter perpendicular distance. This one should be equal to 0. So that means CY is 500 Newton. We already know that CY is 500 Newton. So we can apply the equilibrium equation at joint C. Sigma Fx should be equal to 0. That means since this angle is 45 degrees, 707 cosine 45 minus FAC should be equal to 0. Sigma Fy equal to 0 minus 7 plus 0. So from the first equation, we can define that FAC is 500 Newton. And the direction is right. Our assumption is F member AC is in tensions. So this is right direction. So we find all the forces. CY is 500 Newton. How about the AY? AY, you can see that just the external forces. Then you realize that our assumption for the support reaction at point C was wrong. So AX should be directing this way, and the magnitude should be 500 Newton. AY, because of the CY is positive upward, AY should be downward direction. Because if you look at the joint A, this member BA is in tension, which is the pulling forces upward with 500 newtons. So that's why AY should be downward direction, and it's 500 newtons.